The problem that we will discuss over here is the northwest corner method. Okay, this is one of the methods that is used to find the basic feasible solution for a transportation model, and it may or may not give us an optimal solution. Okay, so the method that we will discuss over here is the first step is to make a matrix between suppliers and destinations. Then the next step, step 2, is to start with northwest corner of the matrix. Step 3 is to see if supply or demand is lesser. Step 4 is when we see that which one is lesser, we allocate it to lesser one. And step 5 is to cross the respective row or column in which demand or supply is allocated. And step 6 is to repeat from step 3 unless all demands and supply are met. So this is the northwest corner method. We will do an example on it. The example is the page number is 215 and it is 5.3 hyphen 1 sunray transport. Okay, now the problem says that there are 3 silos: silo 1, silo 2 and silo 3. There are 3 silos. Okay, so the supplies are 3 and there are 4 mills to which these supplies are supplying trucks full of grain. Okay, we can make the structure as like this. Okay, now the decision variables as the supplies are 3 and destinations are 4. So the matrix is equal to 3 into 4 and decision variables are 12. Okay, so decision variables are x11, which is from S1 to M1, x12, which is from S1 to M2, x13 from S1 to M3, and x14, which is S1 to M4. Okay, these are the supplies. Now x21 is from S2 supply 2 to the mill 1. X22 is the supply 2 to M2. X23 is from S2 to M3, and X24 is S2 to M4. Similarly, we have a third supply also, so it will be X31, which is S3 to M1, X32, which is S3 to M2, X33, S3 to M3, and X34, which is S3 to M4. So these are the 12 decision variables. Okay, x11, x12, x13, x14, x21, x22, x33, x24, x31, x32, x33, and x34. So these are the 12 decision variables that we will find over here. The values of these we will actually find in this question. Now, we will further explain the question. It says that the cost per unit truck. Okay, now the cost, we know that the node carries two, the arc carries two kind of information. The first is cost and the other is the quantity. So we need to find the quantity, but the cost is given to us. So it says that the cost for x11 from silo 1 to M1, the cost is $10, and $2 from S1 to M2, and $20 from S1 to M3, and $11 S1 to M4. Similarly, from S2 to M1, it is $12 and $7 for S2 to M2, and $9 from S2 to M3, and $20 from S2 to M4, sorry. Okay, and similarly from S3, we have $4 from S3 to mill 1, and $14 it cost from S3 to M2 per truck, and $16 of cost from S3 to M3, and $18 from S3 to M4. So now we have all the costs, the 12 costs for the decision variables. Now we will find the objective function. Objective function is the thing is that the professor will mainly want you to do it, you know, it will give you somewhat data like this. Okay, it will be in gradient form, the matrix form. Okay, and he will tell you, yes, yes, and then you will have to make the objective function and constraints. That will all you have to do. You don't have to solve it, or he will give you the all these things, and he will let you know that ask you to solve it using some method. So either one thing, either solve it or either just model it. So the objective function here is 10 x11 plus 2 x12 plus 20 x13 plus 11 x14 plus 12 x21 plus 7 x22 plus 9 x23 plus 20 x24 plus 4 x31 plus 14 x32 plus 16 x33 plus 18 x34. So this is the objective function and subject to. Now we have two kind of constraint. The first is the capacity and the second one is the demand constraint. Now the capacity, first we will consider the capacity. Okay, S1 has capacity of 15 trucks, S2 has capacity per day of 25 trucks, and S3 has capacity of 10 trucks. So these are the capacity constraints. So first taking the capacity constraint. Now S1 transfer ships to all the four silos. Okay, so these summation of these, it must be less than or equal to 15. So we can say that x11 plus x12 plus x13 plus x14. We took I is equal to 1 for all, which means that all the supply is from S1 to M1, M2, M3, and M4. It must be less than or equal to 15 trucks. Similarly, X21, X22 plus X23 plus X24. It means that all the supplies are from the silo 2. It must be less than or equal to 25. And X31 plus X32 plus X33 plus X34, it must be less than or equal to 10. So these are the capacity constraints. Now we will go to the demand constraints. We know that the demand for M1 is 5 trucks. Okay, for M2 it is 15 trucks is equal to M3 is equal to M4. So all the last three, M2, M3, M4, each has a demand of 15 trucks. Only M1 has demand of 5 trucks. So now we know that M1 receives from all these four. So it will be X11 plus X21 plus X31 plus X41 less than or equal to 5. Let me change the ballpoint. Just a minute, please. Okay, so here now the M2 receives from all four, so it will be X12 plus X22 plus X32 plus X42. It must be less than or equal to 15. Similarly, X13 plus X1 X23 plus X33 must be less than or equal to 15. And x14 plus x24 plus x34 must be less than or equal to 15. So these are the demand constraints. Okay, now once we have all this data, okay, this is now actually modeled. So the professor might ask you just to make this thing or do the next step, which I will do right here. So we have S1, S2, and S3, and we will make the exact matrix that is given to us in the question. And we have 4 demands over here. We will make 4 partitions. This is M1, this is M2, this is M3, and this is M4. And the supply constraints over here is 15, 25, and 10. And here the demand is 5, 15, 15, and 15. And the cost we will write in the corner is 10, 2, 20, and 11. Here we have 12, 7, 9, and 20. And here we will have 4, 14, 16, and 18. Now we have cost, we just need to allocate some value over here, here, and so on to, to justify or to put that value that is not greater than this one and not greater than this one. So if you see in the first row and first column, okay, we see that the demand is 5 and the supply is 15. So in this column, actually, we will start from this northwest corner. Okay, this is the first corner that we will start from. So here it is 5 and it is 15. So at this point, we can only allocate 5. And when we allocate 5, it means that we cannot allocate over here and we cannot allocate over here because the demand 5 for M1 is met. And this is the 5 that is allocated. Okay. Now, when the row demand, when the column demand is met, we move to in the horizontal direction, in the rightward direction, okay, in the horizontal one. Now, we see that 5 is already over here. So here the demand, the supply actually is not 15 now. It is 15 minus 5 because 5 is already allocated. So in this row, actually, we can only allocate 10. And here the demand is 15. So we can allocate 10 only over here. Okay, and when we allocate 10, this is 5 and this is 10. So it will meet the exact quantity 15 over here. So we cannot allocate over here and we cannot allocate over here because 15 is already met over here. Now we will move downwards. We can only move downwards. We cannot move in this direction. Okay. Now 10 is already allocated and the total capacity or total demand is 15. So only 5 is left. Okay. We can only allocate 5 in this cell. So when we allocate 5 in this cell, it means that 10 plus 5 is 15. This 15 is already met. So we cannot allocate over here. Okay. We will then move in the right horizontal direction. Okay. Now here we have 5 is already allocated and we have the capacity of 25. So it means that 20 can be allocated over here. But the capacity or the demand in this row, this column is actually 15 and the capacity lift is 20. So we can, because 15 is less than 20, so we can allocate only 15 over here. Okay. Now that 15 is allocated over here, we cannot move downwards because 15, this demand is met. So we cannot move downward, but 15 plus 5 is 20 and we have 5 left over here. So we can allocate 5 over here. We can move in the horizontal direction and we can allocate 5 over here. So we will, when we allocate 5 over here, we see that we have already allocated 5, 15, 20, 20 and 5, 25. Okay. So within, we will move in the downward direction. Now we have already allocated 5 over here and the total demand is 15. So 10 is already left over here and 10 is the capacity over here. So we will put 10 over here. So that is how we solve this northwest corner method. Okay, now the cost is 10. So the Z value for this feasible solution is 5 into 10 plus, here we allocate 10 and the cost is 2. So 10 into 2 plus, here we allocate 5 and the cost is 7. Here we allocate 15 and the cost is 9 plus 5 into 20 plus 10 into 18. So we get 50, 20, 35. This will become 15, 9, 5, 45, 4, 9, $135. Here it will become 100 plus 180. So it will give us 70 and 100. 70 and 135, 205. 205 plus 100, 305, 305 plus 35. 340, 340 plus 420, and it will give us something around about $520. This is the minimum cost that we can achieve. This is the best feasible solution for this problem using the northwest corner method. You got the point? The whole process? The other method will not be same. Actually, in the other method, we will look at the cost rather than the direction and supply and demand. For this, I will give you a question, for practice. Don't worry. Yes, I will write a question and you can practice. Well, for that, I don't. Uh, so in this chapter 5, what did he do actually? He did some problems. Okay, okay. So then we will also, do. So this is the question that you can do using this method. This is a question that you can solve. The reference is 5.1-1, and the page is 28. Yes, Taha. Yes. So this is okay. The next method is actually the least cost method. Okay. The least cost method. So in this one, actually, in this one, we do not move in certain direction. We pick random costs in row or column, select minimum of it, and allocate according to demand slash supply. When row or column is fulfilled, go for another one and repeat the process. So that is all about the least cost method. I will, do a problem on it, and you can see how it is done. It is very short. I will do it very shortly. These are the demands, and these are the supplies for each. Now, in all of these costs, the minimum is, like in this row, we have 4 minimum. In this row, we have 2, 9, and here we have 11. So among the minimums, we have 2 is the minimum. So minimum cost is from S1 to M2. Okay. And in this M2, actually, the maximum supply that we can do is 15. And here the demand is also 15 for M2. So we can allocate 15 over here. So when we allocate 15 over here, these are cancelled. We cannot allocate in this direction. We cannot allocate in this direction because the supply is has extinguished and the demand is met. Okay. So now 15 is allocated from S1 to M2. Okay. Now among the unallocated, like in this column, this column, and this column, we have 4 minimum over here. Here we have 9 minimum, and here we have 18 minimum. Okay. So 4 is the minimum of all. So now here, if you allocate, this is the supply. The total supply is 10, and the demand is 5. So we can allocate only 5 over here because demand is less than supply. So we can allocate only 5. So when we allocate this, we cannot allocate over here. So here we will cross it. Okay. Now when we do this, this is also met. Okay. And this is now 5. I will say 5 is steric. Okay. Because the supply was 10, but 5 is already allocated. So we have now 5 left over here. Okay. Now among this row 1 is already finished and column 1 and column 2 are finished. We need to allocate only in these 4 cells. Okay. Now among these 9 is the minimum cost. Okay. Now the cost, the demand for this column is 15 and the supply for this row is 25. So 15 is less than 25. So we can allocate the maximum of 15 over here. So when we allocate 15 over here, we cannot allocate over here because the demand is met. 15 is already met. Okay. Now we can only allocate between 20 and 18. But we know that the capacity for S3 is now only 5 left. Okay. And the demand for M4 is 15. So we can allocate only 5 over here. Okay. Because the capacity is only 5 over here now. So we can allocate 5 over here. So the rest 20, 10 that is left actually, because here the demand is 15 and 5 is already met. So we have 10 demand left over here. So that 10 will be done over here. Okay. So now S1 to M2, this is the allocated trucks. Okay. From SN to M2, we allocate 15 trucks, and from S2 to M3, we allocate 15 trucks, and from S2 to M4, we allocate 10 trucks, and from S3 to M1, we allocate 5 trucks, and from S3 to M4, we allocate 5 trucks. Okay. Now, S1 to M2 is X12. S2 to M3 is X23 decision variable, and this is X24, this is X31, and this is X34. Now the total cost for X12 is $2. So it will get 15 into 2 plus 15 into X23 is $9 into 9 plus X24. X24 is $20. So 10 into 20 plus 5 into 4 plus 5 into 18. So it will give us 30 plus 135 plus 200 plus 20 plus 18 into 5, it becomes 90. So we get total of 250 over here, 250, 340, 440, and $475. So it gives us somewhat less cost than we previously done with the northwest corner method. It gave us 520, while here we get $475. So we can say that the least cost method is more appropriate, or we can say that it is more efficient than the northwest corner method. Yes, I did it with a different method. Just to compare the cost that we get over here. The previously we got 520, and here we got 475. So it means that the least cost method is actually better performing than the northwest corner method. Yes, but the test will give you only one part of it, you know. Either they will give you this table and they will need you to just solve it. Just like I did it, it will be in like in 5 minutes or 7 minutes, and you can come up with a solution. Okay. Or no, no, he will not say that. He- yeah, he will ask you, most probably he will ask you to model it. He will give you a definitive question, a descriptive question in the descriptive form, and he will ask you to just model it, make a mathematical model of it. Yes. So you need to practice, both the things. But I think the mathematical modeling, that one is, very crucial or important, I can say. You need to know how to model, a transportation model. Once you have modeled it, then solving is quite easy. You can do it by Tora or any another software. Yes. And the third one is the Vogel approximation, but I will do it, in the next session, okay? Because we are already on 42nd minutes and it's this one. Okay. Okay. Now, the first thing that we see over here in this matrix is to see what is the least cost. We see that the least cost here is $2, which is from S1 to M2. Okay. Yes, we can pick that. Yes, we can pick that. For example, this was 4 and this was $2. So I would have picked this one. Yes. So when we the important thing is that when you allocate the value, you must know what is the demand in the column and what is the capacity in the row. So here the capacity is 15 and the demand is also 15. So we can allocate a total of 15 over here. So when we allocate 15, we cannot allocate in anymore in this whole row, and we cannot allocate in this column. So this column and this row is cancelled. That is the thing that you need to know. You know, we see that the demand is 15 over here and the supply is 15, and we allocated 15. So we cannot, allocate any value over here, here, or here, and we cannot allocate over here or here, not downward and not in the horizontal position. So we cancel that column and that row. Now the second least cost is 4. Okay, the supply over here is 10, but the demand is 5. So we can allocate only 5 over here because demand is less than supply. Okay, so when we actually, so just you know just having a general repeating the general idea of it. We already allocated 15 over here because the cost over here was $2. Okay, now we cannot allocate in this row and this column because 15 is the supply, maximum supply. So 15 is already allocated. So we don't have any more supply to allocate in this, or in this. And similarly, the demand here is 15, but demand is met. So we do not need anything to be allocated in this column actually. Now the columns left are this one, the third column and the fourth column, or the second row and the third row is left. Okay, excluding the second column area. Now the capacity is in this row because we have to supply it from S3 and the S3 capacity is 10. Okay, so we will allocate 5 over here and 5 capacity will be left over here. So when we allocate 5 over here, we cannot allocate any more in this column because the demand is already met. Now we will move to these four. Okay, because this row is already done, this column is done, and this column is done. So we have only these 4 cells need to be filled. Now, if you see this is $9, $20, $16, and $18. Now the minimum is $9. The capacity, because it has to be bit from silo 2, so the silo 2 has capacity of 25 trucks, and the demand over here for M3 is 15. So we can maximum allocate 15 over here because demand is less than the supply. So when we allocate 15 over here, this whole column is now blocked. We do not need to put any or make any allocations over here. We cannot make. So only 2 cells are left over here. Now when we allocate 15 over here, okay, this has 25 capacity. So the total capacity left is 25 minus 15 is equal to 10. So in this row, we can allocate only 10. And in this row, we can allocate only 5. Okay. Now moving to this column, actually, we have 18 is minimum is less than 20. So we can make the first allocation over here. Here the capacity left is 5 and the demand is 15. So we can allocate a maximum of 5 over here. So when we allocate 5 over here, okay, the demand remaining is 15 minus 5 is equal to 10. So we can allocate only 10 over here. And 10 is also the capacity left. So we allocate 10 over here. So when we multiply these allocations with the respective costs, we get a total value of $475. So that is how we get a solution using the least cost method. The next method that we will do over here is Vogel approximation. Okay, this is a kind of complex method from both of these two. Both of these two are simpler methods. This Vogel one is a bit complex from both of them. I will explain it on the next page over here. Vogel. Okay. It is also called WAM, Vogel approximation method. Okay. So it has generally 3 steps, okay, to follow. The first step is, step 1 is you need to determine or find the penalty for each row and column. Okay, and this penalty is equal to second least cost minus the least cost that we have in that column or that row. Okay, now when we find these penalties, we move to step 2. Okay, and the step 2 is to identify the row or column with the largest penalty. We pick the row or column with the largest penalty, and when we find the largest penalty, we make the allocations in that particular row or column, but that allocation is constrained. It means that you have to look for the supply and demand and act accordingly. You have to make the allocations according to the supply and the demand, just like we did in the least cost method and the northwest corner method. Okay, and if there is a tie between the penalties, because like in row 1 we have like penalty of 5, and in the column 2 we also have the penalty of 5, so we can make the the choice arbitrarily. We can choose either column 2 or the row 1, so that is okay. Okay, we break the tie using the arbitrary method. We arbitrarily choose between the ties. Okay, and then we adjust the supply and demand accordingly, just like I wrote over here, say that it has to be constant. You have to adjust it for the supply and the demand remaining. Okay, you cannot make over allocation at any point. You will have to in the demand and in the supply constraint. And when we make the allocations, we move to the step 3. The step 3 is, if exactly one row or column with zero supply or demand remains uncrossed, then stop. Stop when you have exactly one row or column left with zero demand or supply. Okay. Now we will, apply these tips to this particular case, and we can. I will explain it. Meanwhile, I am doing the problem. Okay. Now the question is same actually. We have 3 suppliers and 4 destinations. Here the cost is 10, 2, 20, and 11, 12, 7, 9. Yes, yes. You will apply. Yes, the question I gave you, you should apply all the three methods and determine like which one is the best, to consider. Which one gives you the minimum cost. So you will understand the process and also the benefits of it, like how it is more appropriate or more efficient. These are the supplies and the demands are 5, 15, 15, and 15. Now we will use the WEM or the Vogel approximation method to find the minimum cost of distribution. Now, as we say in the first step, is to determine the penalty for each row, and the penalty is equal to the second least cost minus the least cost. Okay, so in this row, if you see, the least cost is 2 and the second least cost is 10. So the penalty in row 1 or 1 is equal to 10 minus 2, so it becomes 8. So 8 is the penalty for row 1. For the row 2, the least one is 7 and the second least is 9. So we can say that 9 minus 7 is equal to 2. So the penalty This is the penalty column. Okay, the penalty for row 2 is 2. For the third row, the least is 4 and the second least is 14. So 14 minus 4 is equal to 10. The penalty for the third row is actually 10. Now getting it for the columns. This is the penalty row for the columns. Okay. Now here the minimum is 4 and the second minimum is 10. So 10 minus 4 is equal to 6. In the second row, the minimum is 2 and the second minimum is 7. So 7 minus 2 is equal to 5. Now in this one, the minimum is 9 and the second minimum is 16. So 16 minus 9 is equal to 7. Now in this one, the minimum is 11 and the second minimum is 18. So 18 minus 11 is equal to 7. Now we see that the third row has a penalty of $10. Okay. And in the columns, the maximum we get is 7. So 10 is greater than 7 actually. So we will make the allocations in the third row. Okay. Now in the third row, actually, the minimum is $4 over here. Okay. So we will make the allocations over here. But how much allocation we can make? The number of allocation, the number of trucks that we can unload over here or transport over here is 5 only. So we will make the allocation of 5 over here. So when we make this allocation, this whole column is crossed because we cannot make any allocation in this column because already the demand 5 is met. Now we have 3 into 3 matrix that we need to look for, or now we already made the allocation which is from S3 to M1 and the location is 5 trucks. Now the matrix have been reduced. Okay, this is S1, S2 and S3 because the demand of M1 is already met. Okay, so we will eliminate or we will ignore actually this column. Okay, so ignoring this column we get this exact matrix 2, 20, 11, 7, 9, 20, 14, 16 and 18. Now again we will determine the penalties. Okay, now the supply over here is 15, over here the supply is 25, but here the supply is only 5 because we already allocated 5 over here. So here the supply was 10, so it will be reduced to this is supply actually. The supply is 10, so it will be reduced to 5 only. Okay, so here now the supply I will say 5 steric because we allocated out of it 5. So now the penalties, calculating the penalties. Now here the minimum is 2 and the second minimum is 11. So 11 minus 2 is equal to 9. Here the minimum is 7 and second minimum is 9. So 9 minus 7 is equal to 2. In the third one, we have 14 as minimum and 16 as the second minimum. It will also equal to 2. Now for this is 15, 15 and 15 as demand. And we already met the demand 5 over here, so we will ignore that. Okay, now the penalties for the columns are the minimum is 2 and the second minimum is 7. So 7 minus 2 is equal to 5. So 5 is the penalty over here. Here the minimum is 9 and the second minimum is 16. So 16 minus 9 is equal to 7. And here in the third column, we have minimum equal to 11 and second minimum is 18, which will also give us 7. Now we see that 9 is the maximum penalty over here. Okay, so we will make allocation in row 1. Now here the minimum cost is 2. The maximum supply available is 15 and the demand is also 15. So we can make allocation of 15 over here. So when we make the allocation of 15 over here, we cannot make more allocation in this row and this column. So this row and this column is now cancelled. We have now 2 by 2 problem left. Okay. And the second allocation that we make is from S1 to M2 and the allocation is 15 trucks. Okay. The first allocation that we made was 5 trucks from S3 to M1 and the second one is from S1 to M2. Now we will make another table which is only 2 by 2. Now S1 is cancelled out. We have only S2 and S3 left and M3 and M4 left over here. Okay. Now for M3 and M4 and S2 and S3, the cost is here is 9, 20, 16 and 18. Okay. And the capacity, supply or capacity for the S2 is 25 and for S3 is 5. I will say put asterisk over here because we already allocated 5 from this. So the penalty, the row penalty will be 20 minus 9 is equal to 11 and 18 minus 16 is equal to 2. Okay. Now the demand over here is 15 and over here is also 15. Now for the column penalty, we have 16 minus 9 is equal to 7 and 20 minus 18 is equal to 2. Now 11 is the maximum penalty over here. So we will allocate in this row. Okay. Now 9 is the minimum over here. Okay. And the maximum that we can allocate over here is 15. So when we allocate over here, this column will be cancelled out. Okay. We have only 1 into 2 now left. Okay. And the penalty is not working now because we have only one cost left. Okay. So 20 is the cost over here and 18 is the cost over here. So 18 is less than 20. So the next allocation we will make is over here. And the maximum allocation that we can make is 5. The demand is 15, but the supply is 5. So we can put only 5 over here. And we have already allocated 15 over here. Then supply is now here is 25 minus 15, 10. So we can apply 10 over here. So now the allocations made are S2 to M3, we made 15 allocation. And from S2 to M4, we made 10. And from S3 to M4, we made 5. Now we will, find the total cost. Now, the cost from S3 to M1, S3 to M1 actually, from S3 to M1 is $4. So Z is equal to 4 into 5 plus the second allocation that we made is from S1 to M2, which is 15, and the cost is $2. So we will add 15 multiplied by 2 over here, and the next allocation that we made is from S2 to M3, which is 15, and the cost is 9. So it is 15 into 9 plus the next allocation that we made is 10 from S2 to M4, and the cost is 20. So we will have 10 into 20 plus the other allocation we made is 18 into 5. So we will make 5 into 18, and the total cost is 20 plus 30 plus 135 plus 200 plus 18 into 5 is $90. We have 50 plus 200 250 plus 90 340. So 340 plus 135 is equal to $475. So Vogel is equal to least cost in this case, because Vogel is also giving us $475, and the least cost method that we done over here is also giving us $475. So both are giving the same cost over here. You understand the process? Okay, that's great. So I will select a problem from the other book, and we can make a mathematical model of it, just for the sake of understanding how to make the mathematical model. Yes, because the teacher will most probably he will ask you to make mathematical model. And then we will start the network models, and in that the teacher has done only the one problem, the shortest route problem, as I see in your notebook. So I will just introduce make an introduction of the network models, how they are used and all that, what are they and how they are used, and then I will just skip towards the shortest path problem. It's also called the Dijkstra model. Dijkstra algorithm. It is used for the shortest route, to find the shortest route between the origin and the final destination. Yes, and that question is done actually by the professor. I saw it in your notebook. So I will focus on that. In all the problems, I will focus on that particular thing. Okay. Okay. So this is a problem 7.1. I will send you the screenshot of it. Okay, after the session is over. Okay. So you can also model it without looking at. Yes, sir. I will write. The problem is power co-formulation, and it tells us how to formulate a transportation model. It says that PowerCo has 3 electric power plants. Okay, the number of power plants is equal to 3 that supply the needs of 4 cities. The supply is made to 4 cities. It means that, just for your, understanding, when we say that we have 3 supplies or 3 power plants and 4 cities, it means that it will make a 3 into 4 matrix. So the number of decision variables will be 12. Okay, each power plant can supply the following number of kilowatt hours of electricity. Okay, so we can write it as plant 1, plant 2, and plant 3. We can write capacity over here, and below the capacity I will write the respective capacity. Plant 1 can supply 35 million kilowatt hour. I will say here in millions. Okay, the power plant 2 has a capacity of 50 kilowatt hours, but in millions. Okay, and the third one has 40 kilowatt hours, 40 million kilowatt hours. So these are the capacities of the 3 plants. Okay, now the peak power demands in these cities which occur at the same time are as follows. So in the same kilowatt hours, the city 1, I will now write the demands, and the demands for city 1, city 2, city 3, and city 4 are 45 million kilowatt hour, city 2 has a 20 million kilowatt hour, and city 3 has 30 million kilowatt hours, and city 4 also has a 30 million kilowatt hour. Now in the question we have the essentials, the basics of the transportation model. We have the number of suppliers, the number of destinations. Okay, we have the capacities, we have the demands. The only thing left is the cost. Okay, now the total cost, actually, the cost in dollars from plant 1 to city 1 is $8. From plant 1 to city 2 is $6. Okay, from plant 1 to city 3 is $10. From plant 1 to city 4 it is $9. This is from the plant 1. From the plant 2, P2 to city 1, P2 to city 2, P2 to city 3, and P2 to city 4. These costs are 9, 12, 13, and $7 respectively. Now for a third power plant, we need to define the cost. So P3 to C1, P3 to C2, P3 to C3, and P3 to C4. The costs are actually $14, $9, $16, and $5 respectively. Now we have the cost, the capacities, and the demands. Okay. Now the basic logic is that you must define the decision variables. So here the number of suppliers is equal to 3 and the number of destinations is equal to 4. So the number of decision variables is equal to 12, 3 into 4. Okay. Now X11, we define it as from power plant 1 to city 1. X12, we define it as power plant 1 to city 2. X13, we define it as power plant 1 to city 3. And X14, we define it as power plant 1 to city 4. Similarly, X21, we define as P2, power plant 2 to city 1. X22 is defined as P2 to city 2, and X23 is defined as P2 from power plant 2 to city 3, and X24 is defined as from power plant 2 to city 4. Similarly, X31 is from P3 to C1, X32 is from P3 to city 2, and X33 is from P3 to city 3, and X34 is from P3 to city 4. So these are the decision variables. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here the calculation that we made for the number of decision variables, it stands true. We have 12 decision variables now. So the objective function can be written as costs are the concern over here, so it will be a minimization function. And also the transportation models are all the minimization problems. Okay. So the first cost that we have is $8. So 8x11 plus 6x12 plus 10x13 plus 9x14 plus, now for P2 we have 9x21 plus 12x22 plus 13x23 plus 7x24 plus, now for power plant 3 we have 14x31 plus $9 x32 plus $16 x33 and plus $5 x34. So this is the objective function, and it will be subject to, we will have two types of constraints over here. The first one is the capacity constraints, and the second one is the demand constraint. So the capacities for the three power plants are 35 million kilowatt hours, 50 million kilowatt hours, and 40 million kilowatt hours. Now, as the power plant 1 supplies to all four cities, so it will be X12, 11 plus X12 plus X13 plus X14. It must be less than or equal to 35. Similarly, X21 plus X22 plus X23 plus X24, it must be less than or equal to 50 million kilowatt hours. Similarly, X31 plus X32 plus X33 plus X34, it must be less than or equal to 40. So these are the capacity constraints. Now we will go to demand constraints. The demand constraints are the power supply that each city is getting from each power plant. So the city 1 is getting from plant 1, plant 2, and plant 3. So it will be X11 plus X21 plus X31, and it will be equal to 45 kilowatt hours. x12 plus x22 plus x32, it must be less than or equal to actually 20 kilowatt hours, and x13 plus x23 plus x33 must be less than or equal to 30 million kilowatt hours, and x14 plus x24 plus x34 must be less than or equal to 30 kilowatt. Now can you hear me? Can you hear me now? Yes, I have headset. Okay. So here these are the capacity constraints and these are the demand constraints. And we have all xij for all I is equal to 1, 2, 3 up to m, and j is equal to 1, 2, 3 up to n. It means that for m power plants and n cities must be greater than or equal to 0, which is the non-negativity constraint. And it is, you must have like, this constraint in each of the mathematical model. So that is how we model a transportation problem. Okay, I will explain it. Okay, so this is the power plant power co-formulation. Okay, we have the number of power plants is equal to 3, and the number of cities to which this power is transferred is 4. So the total number of decision variables will be 3 into 4 or 12 decision variables. Okay, now the capacities are given. Plant 1 has a capacity of 35 million kilowatt hours. Plant 2 has a capacity of 50 kilowatt hours in millions. Okay, and plant 3 has 40 million kilowatt hours. These are the capacities of the 3 plants. Now the demands for each city that this power is transferred to is, for city 1 the demand is 45 billion kilowatt hours. For city 2 it is 20 million kilowatt hours. For city 3 it is 30 million kilowatt hours, and for city 4 it is also 30 million kilowatt hours. Like today from the app, it just connected. Yes, it was good today. So yeah, these are the demands for the 4 cities. Now to transfer or to ship this power to each city, we have some costs associated because this is a transportation model. So there are always costs associated. So these are the costs associated for transferring from power plant 2 to city 1. It is $8 per kilowatt hour, and the shipment charges for from power plant 1 to city 2, it is the $6. From power plant 1 to city 3 it is $10, and from power plant 1 to city 4 it is $9. Similarly, from power plant 2 to city 1 it is costing us $9 per kilowatt hour, and from power plant 2 to city 2 it is $12 per kilowatt hour. Similarly, from power plant 2 to city 3 it is $13, and from power plant 2 to city 4 it is $7. And from power plant 2 to power plant 3 to city 1 is $14. Power plant 3 to city 2 is $9. For power plant 3 to city 3 is $16, and for power plant 3 to city 4 it is $5. Now we will take these costs and we will define the decision variables and put it into the objective function. Now we say that, let's suppose x11 is the number of kilowatt hours transferred from power plant 1 to city 1, and x12 is the number of kilowatt hours from power plant 1 to city 2, and so on. And we say that x21 is the power. Yes, assumptions, but the assumptions are in the, if you understand the generic form of it, the generic form is that Xij is the number of units transferred, okay, where I is the power plant and J is the city number, okay. Do you understand the general form of it? Okay, so now here in this one, I is equal to 1, 2 and 3 because we have 3 power plants, and J is equal to 1, 2, 3 and 4, okay. Now X11, it will denote from power plant 1 to city 1. Similarly, X12, if you put I is equal to 1 and J is equal to 2, it means that the number of units from power plant 1 to city 2. Okay. If we put I is equal to 1 and J is equal to 3, it means that the number of units transferred from power plant 1 to city 3 and so on. So these are the same. I wrote it in the general form. It is derived from this general annotation. Xij is equal to the number of units, while I is equal to the power plant and J is the city number. And I is equal to 1, 2, 3 and J is equal to 1, 2, 3, 4 because we have 4 cities, and I is equal to 1, 2, 3 because we have 3 power plants. Okay. So from this general annotation, you can say that X11 is the number of units from power plant 1 to city 1, and so on up to X34. X34 will denote actually from power plant 3 to city 4. This is simple if you understand the general generic form of it. Okay. Now we define the objective function of it. As the costs are the concern over here, so we have the minimization problem. So it is minimize Z is equal to, now we have the cost associated with each kilowatt hour transferred because we have cost over here. Here we have the transportation cost. So whenever there are costs associated, it means that it is a minimization problem. Yes. Yeah, so this is the cost for each of the kilowatt hour that is transferred from each power plant to each city. So 8 into X11 means that $8 is the price for each kilowatt hour transfer from power plant 1 to city 1 because it is X11, and $6 from power plant 1 to city 2, $10 from power plant 1 to city 3, and $9 it costs to transfer from power plant 1 to city 4 and so on. Okay, so we write the objective function just like this. Okay, now it is subject to two main constraints. The first one is the capacity constraints and the second one is the demand constraints. So in the capacity constraints, okay, it will be for power plant 1, 2 and power plant 3. Okay, so we know that I is equal to the power plant. So the capacity constraint actually, it will have 1 over here at each decision variable. We have x11, x12, x13 and x14. We know that here is 1 preceding the second number. It means that it is the capacity of the power plant 1. In the second one, we have x21, x22, x23, x24. 2 means that this is the power plant 2 capacity. So it must be less than 35, 50 and 40 respectively. Okay. Now for each city, we get the power from 3 power plants. So for city 1, the demand will be less than or equal to 45 kilowatt hours. So X11 is the number of units or number of kilowatt hours that it gets from power plant 1 X21 is the number of kilowatt hours that CT1 gets from power plant 2, and X31 is the number of kilowatt hours that CT1 gets from power plant 3, and it must be less than or equal to 45. We see that the second number is 1, 1, and 1 over here. It means that it is demand for CT1. Here we have the second number as 2, 2, and 2 over here. It means that it is representing CT2. Here we have the second number is 3, 3, and 3 over here. It means that it is representing CT3. And at the fourth one, we have 4, 4, and 4 over here. So it means that it is representing CT4. So that is how you come up with the objective function and demand and capacity constraint. Now you understand it? Okay. That's great. That's great. You should practice it. Like, I will send you some questions, from the other book also. You can practice it and you can send it to me. So, I will see it and I will let you know if there is any wrong with it and, if you make any mistake in it. Yes. So that is all about the transportation models. We have three basic general methods to find the basic feasible solution. The first one was the least corner method, the northwest corner method. The second one was the least cost method, and the third one was the WAM, which is also called the Vogel approximation method. Okay, so I sent you a question. You should, perform all these three methods on the same question and come up with solution and compare the solution with each method. So you can, know that which one is more, efficient in calculating the least cost. And with that, we will move to the another chapter, which is the actually the network models. Yes, we have only one, we will do only one lecture on the network model, only one lecture, not more than that, but just to do what your teacher have already done. So, because he has done the Dijkstra algorithm and, the shortest path method, SPM. Yeah, or SPT is also called SPT. So these two things are done by your teacher. So I will just, do these two things in one lecture, and then we can move to the non-linear part of the mathematical programming. Yes. So I think we should now, end the session, and tomorrow we can come up with a new lecture, or what you say, what you suggest. Okay. So I will do this session also. Let me, open the network model chapter. Yes, it is very crucial, for you to practice it and, make the best out of, your capabilities. Because if you do not practice it, then, I'm sorry, but, these are the things that are quite, dry. If you do not practice it, you will not, understand it, and you will not perform it in the exam actually. You will be, left blank if you do not practice it. So that is quite important thing in the, operation research. Even my friends in the industrial engineering department, they actually fear this particular subject. They don't like it because this is a kind of thing that that people actually don't get very easily. And when they get it, yes, yes, yes. For with time it will grow on you, and you can then try to think about things that it's a just or it the studies. Okay, so let's start with the chapter 6 in the Taha book, which is the network models. Okay, so now as the name suggests, it means that we will have a series of operations or a series of events that are happening. Okay, for example, and it will form a shape of a network. For example, in for example a Kuwait city, you for example this is your house, this is your home from where you start. Okay, I will state it as 0 node or node 0. Okay, and you want to visit a particular place. For example, you want to this is point A and this is point B. You want to visit like university, the Kuwait National University you want to visit. Okay, now this is your home and this is the destination. Okay, now between these two points or these two nodes, there are a lot of ways that you can reach this point. Okay, for example, one of the point is that you get to point one. Okay, which is a bus station, for example. Okay, and then you pick a car. Okay, and then you go to for example certain place which is for example uh, a park. Okay, and when we reach this park, okay, this is for example point 3 is the park. Okay, and when we reach this park, and then from this park we can come up to university. Now there is another way, you know we can have another way, which is we go to node 2, which is a shopping mall area, and then from there straight on you go to university. And we have a third one. Okay, we get to a point which is for example point 4, and it is some school. Okay, this is some high school. Okay, and from this you reach, you go to the park, and from that park you reach the university. Now there are three networks. From point A to point B, you have three alternatives to reach the point B. Okay, the first one is passing through point 1, then to point 3, and then to point B. And the second alternative is you go from point 0 to 2 and then directly to point B. The third alternative is you go to point 4, then go to point 3, and then go to point B and reach your destination. So the network model is analyzing these alternatives actually for cost minimization. Okay, and cost over here, it may be the time duration, because most of the time we say that okay, if we uh, do you use Uber or Kareem or Google Maps? I'm asking if you use Google Maps or Google, Kareem or Uber service. Okay. So, okay. When you use Google Map, actually, it will always give you some alternative. Like you can also go through this path, and this is like 5 minute shorts or 5 minute long. Yes. So this network model is actually the same as the Google Map that is showing you alternatives that if you follow this path, you can reach this destination like 5 minutes earlier than this path, the alternative B. Okay. So network model is all about exploring these alternatives and find the alternative that is costing you the minimum. The cost may be in the context of time. It can, for example, if you go to point A, 1, 3, and B, you have like A, 1, 3, and B. For example, this gets us in 17 minutes, okay? And A, 2, and B, this gets us in 21 minutes. And A, 4, 3, and B, it gets us in 23 minutes. Okay. So now there are three alternatives and you have time for each. So this is the time alternative. Okay. Similarly, for this, for example, the cab will get, he will charge you $15. Here it will charge you $12. And here he will charge you $11 because it is the part that is used by the public transport. A bus or train goes from point 0 to point B through point 4 and 3. And it is, so now if you are taking the time alternative, then this one is the best method to go from point A to point B because it is consuming the less time, 17 minutes only. But if it comes to dollars, if it comes to cost, then and using the public transport, you can go from point A to point B where this point 4, 3, and B, and it will cost you $11. So this is the best alternative in terms of money value. So it is all about the perspective or the context in which the problem is taken. And the network model is actually analyzing the alternatives for minimum cost. The cost may be time, the cost may be, dollars, the cost may be, the spanning of it, like, the duration of it. So that's how these problems are dealt with. Now, we will define the scope and definition of the network models. For example, you design a natural gas pipeline offshore network. Okay. So what you want to do is, for example, this is the point that the offshore well is, and here is the point 2, where you want to get the gas. Then you must design the network in certain way that it gets in the minimum time. Okay, so this is one of the scope of the network models. Determination of the shortest route between any two cities. Okay, shortest route between two cities. This is one of the scope of the network models. Determination of maximum oil that you can get from an oil well or network. This is the scope of the network model. Time scheduling. Time scheduling is also, a scope of the network model. and determination of the minimum cost flow. The minimum cost flow is also, it is used in the oil refineries, and this is also a scope of the network models. Now, the algorithms actually that are the concern in minimum spanning tree and these problems, there are four kind of algorithms that are used. Okay, the first one is the minimum spanning tree. It is also called MST. Okay, the second one is shortest route algorithm. It is also called SPT. Okay, the third one is the maximal flow, and the fourth one is the CPM, which is also called critical path method. This one particular is used in the project management. You must have, done some work in Primavera. You know Primavera? Because yes. So CPM actually it is applied in Primavera and it schedules you, it gives you the maximum possible time and the minimum possible time for any project to complete and the resources that will be used, over the time. So CPM is actually used over here, which is called the critical path method, and it allow us to see what is the minimum possible time that in a project, for example, building a bridge or making a refinery. So this gives us the minimum time that it can be accomplished. A project can be accomplished with all the resources constraints. So these are the four actual algorithms that are used in the network models, and our particular is the shortest path method or the shortest route algorithm SPT that we will focus on over here. Okay, we will not do the minimum spanning tree or maximal flow or CPM, but we will do only the shortest route algorithm because the teacher has done only this thing in the lecture. He has skipped all the other three. Okay, now what we mean by network. A network is actually set of nodes and arcs. Arcs can also be, defined as branches. Okay, and we have two kinds of arcs. The first kind is directed, and the second one is non-directed. Directed is when we have like a specific direction of, like pointing from point A to B. This is the directed one. Now, and we have like point A and B, and we have just a simple line in it. This is the non-directed. It means that it has two-way direction. And we have, if it is like this, it means that the information or the material or the cost flows only from point A to B, and it is not reverse. It is not flowing from B to A. Okay, so this is the directed one, and this is the not directed one. Okay, so it gives us the orientation whether it is a positive flow, negative flow, or bidirectional flow. Okay, and the path is actually is the set of arcs joining distinct nodes. This is another node. This is node 1, this is node 2, and this is arc. Here the arc will carry the information. It's okay, the arc carry the information. And the second information that arc the flow, it will show. Okay, now I will go towards the shortest route problem. Okay, okay, what does the shortest route problem? Okay, brother, this is the example of the MG autos. Okay, we had 3 supplies and 2 destination, which is Denver and Miami, and the supplies were for Los Angeles, Detroit plants and New Orleans plants, and these were the capacities of respective plants. The LA plant has a capacity of 1000 cars, Detroit has 1500 cars capacity, and New Orleans has 1200 cars capacity. Okay, these capacities will make us the supply constraints. Okay, now the demand for Denver is 2300 cars, and for Miami it is 1400 cars. These things, these will make the demand constraints. Okay, and these are the miles that each car has to travel. From Los Angeles to Denver it has to travel 1000 miles, and from Los Angeles to Miami it is 2690 miles. From Detroit to Denver it is 1250 miles, and from Detroit to Miami it is 1350 miles, and from New Orleans to Denver it is 1275 miles, and from New Orleans to Miami it is 850 miles. Okay, now we see that if we add the demands, it is 3700, and if we add the capacities, it is also 3700, which means that demand is equal to supply. These kind of problems are called balanced models, and if demand is not equal to the supply, then these are unbalanced models. We need to add dummy supply or dummy destination depending on which one is greater or lower. Okay, now these are the cost of transportation per mile per car, which is 8 cents, which makes up to $0.08 per car per mile. Now the total mile from LA to Denver is 1000, so we multiply 1000 with 8 cents or $0.08, so it will make $80 a car. So each car from LA to Denver, it takes $80 of cost to reach. Okay, and similarly we also convert these miles into the cost by multiplying the cost with the number of miles, and we get the respective cost per car per car supplied to each of the destinations. So these are the 80, $215, $100, $108, $102, and $68. Okay, now we make a network model of it. Okay, and we say that x11 is the unit transported from LA to Denver, x12 is the unit transported from LA to Miami, x21 is the units transported from Detroit to Denver, and x22 is the unit transported from Detroit to Miami, x31. Similarly, we have 6 decision variables because the matrix is 3 into 2, 3 supplies with 2 demands, destinations. So 3 into 2 is 6 decision variables. Okay, now the objective function, as we calculated the cost per unit car for each of the destination, these will be put into the respective objective function with the respective objective function coefficients. So with x11 from LA to Denver we put 80 because it is 80. From LA to Miami, which is x12, is 215. So 80 x11 plus 215 x2 plus 100 into x21 plus 108 into x22 plus 102 into x31 plus 68 into x32. So this will make the objective function, and as costs are concerned over here, so it will be a minimization function. Okay. Now there are two kinds of constraints over here, the supply constraint and the demand constraint. The supply is that from LA supplies to two destinations, which is x11 and x12. So x11 and x12, it will be less than or equal to 1000 car, which is mentioned over here. So this is first constraint. X21 plus x22, x21 means that from Detroit to Denver, and x22 means from Detroit to Miami. If we add these, it must be less than or equal to 1500 cars, because Detroit can maximum produce 1500 cars. And x31 plus x32, which is from New Orleans to Denver and Miami respectively, it must be less than or equal to 1200 cars. So these are the supply constraints. And now we get to the demand constraints. The demand constraints are that the cars supplied to Denver from LA, Detroit and New Orleans respectively, it must be less than or equal to 2300 cars. So x11, x21 and x31 must be less than or equal to 2300 cars. Similarly, x12, x22 and x32 must be less than or equal to 1400 cars, and all xij must be greater than or equal to 0. It means that they must ship either 0 or greater than 0 cars from each supply to each demand destination. Okay. Now we model this particular mathematical model into the Torah, and we find how what are the values for x11, x22, x21, x22, x31 and x32, these 6 decision variables. So here we have, I will go to the transportation model in the first menu. Okay. Now when we go to transportation model, this transportation input grid is defined, it is given. All these spaces are free. So I put Denver over here, I put Miami in the D2. D1 means the first destination, D2 means the second destination, and in S1 supply 1 I fill with it with LA, supply 2 is Detroit, and supply 3 is New Orleans, denoted by NO. Now AT is the cost per unit car from LA to Denver, and 215 is the per unit cost of each car from LA to Miami. And similarly we put all these values, and in the supply the LA can produce maximum of 1000 cars, while Detroit can 1500 cars and New Orleans can 1200 cars, and the demand for Denver is 2300 cars, we put over here, and for Miami it is 1400 cars, we put over here. And we go to the solve menu. Okay, we do not want to save the data, so I will say no over here, and we go to solve problem and we final solution. Okay, now the final solution is that from S1 to D1, which is x11, it is 1000 cars. So x11 yields a value of 1000. The second one is S2 to D1, which is x21. So x21 is 1300 cars, and the third one is S2 to D2, which is x22, which is 200 cars, and the fourth one is S3 to S2 to D2. Sorry, so S3 into D2, it will make x32, and it is 1200 cars, and the total cost is $313200. Okay, so that is how we get the values. So if I write the same solution into our the x11 form, it will be like this. X11 is 1000 cars, x12 is equal to 0, x21 is 1300 cars, x22 is equal to 200 cars, x31 is equal to 0 cars, and x32 is equal to 1200 cars. Okay, now the total cost is, we just multiply the per unit car cost with the respective figures, and it will give us $3,13,200. Okay, it is 3,13,200. So that is how we get the solution from Torah. Okay, I will make the next video for the algorithm, the northwest corner method.